Magnetic effect of electric current. Oysters' experiment on the magnetic effect of current. Hans Oysters in 1820 in his experiments observed that when an electric current is passed through a conducting wire, a magnetic field is produced around it. The Oysters experiment observations. When the key is open, no current flows. The needle shows no deflection and points in the north-south direction. That is, it remains parallel to wire XY as shown in the figure. When the key is closed, the current flows in the wire in the direction X to Y. The pole north of the needle deflects towards the west as shown in the figure. If the current in the circuit is increased, the deflection of the needle also increases. When the direction of current in the wire is reversed by reversing the connections at the terminals of the battery, the north pole end of the needle deflects towards the east as shown in the figure. If the wire is held below the magnetic needle such that the current is flowing from south to north, then the north pole of magnetic needle deflects towards the east as shown in the figure. If we reverse the current, that is, it now flows from north to south, then the north pole of the needle deflects towards west as shown in the figure. Thus, current or moving charge produces a magnetic field. Observation from Oysters experiment. The deviation affected on the compass needle indicates that the presence of the magnetic field around the conductor which is carrying current. Hence, the needle deflects to align itself in the direction of magnetic field at that point. Thus, any conductor through which current or moving charge flows behaves like a magnet and produces a magnetic field around it. This is called the magnetic effect of current. The strength of the magnetic field depends on the magnitude of the current. More the current, greater is the magnitude of the magnetic field. The direction of deflection of magnetic needle depends upon the direction of the electric current. The direction of deflection of the magnetic needle also depends upon the relative position of the conductor wire with respect to the magnetic needle. Inference: a current or moving charge produces a magnetic field around it. This is called the magnetic effect of current. The strength of magnetic field depends on the magnitude of current and its direction depends upon the direction of the current. Magnetic field lines around a straight current carrying conductor or wire. When a small piece of cardboard sprinkled with iron fillings is placed such that a current carrying conductor passes through the center of the cardboard, as per arrangement shown in the figure, we observe that the magnetic field lines are in the form of concentric circles around the wire, with their plane perpendicular to the straight wire and with their centers lying on the wire. When the direction of current in the wire is reversed, the pattern of iron fillings does not change, but the direction of deflection of the compass needle gets reversed. The north pole of the compass needle now points in a direction opposite to the previous direction, showing that the direction of magnetic field has reversed. On increasing current in the wire, the magnetic field lines become denser and the iron fillings get arranged in circles up to a large distance from the wire, showing that the magnetic field strength has increased and it is effective up to larger distance. Right hand thumb rule. If we hold the current carrying conductor in our right hand such that the thumb points in the direction of flow of current, then the fingers that encircle the wire indicate the direction of the magnetic field lines. Magnetic field due to current in a loop. When a loop of wire is passed through a small piece of cardboard sprinkled with iron fillings, as shown in the figure, we observe that in the vicinity of wire P and Q, the magnetic field lines are nearly circular. Within the space enclosed by the wire, that is between P and Q, the magnetic field lines are in the same direction. Near the center of the loop, the magnetic field lines are nearly parallel to each other. At the center, the magnetic field lines are along the axis of loop and normal to its plane. The magnetic field lines become denser, that is, the magnetic field strength is increased if the strength of the current in a loop is increased and the number of turns in the loop is increased. The magnetic field lines pass through the loop in the same direction. They appear to come out from the face of loop on the other side, so that face behaves as a north pole, while the magnetic field lines appear to enter in at that pole. Clock rule. clockwise current south pole and anti-clockwise current north pole. Looking at the face of the loop, if the current in the wire around that face is in anti-clockwise direction, the face has north polarity, while if the current at that face is in clockwise direction, the face has south polarity. Magnetic field lines due to solenoid carrying current. The magnetic field lines inside the solenoid are nearly straight and parallel to the axis of solenoid. That is, the magnetic field is uniform inside the solenoid. The magnetic field lines become denser, that is, a strong magnetic field is obtained on increasing current in the solenoid. The magnetic field is increased if the number of turns in the solenoid of given length is increased. The magnetic field is also increased if a soft iron rod core is placed about along the axis of solenoid. The soft iron increases the strength of magnetic field of the solenoid, as the soft iron has a high magnetic permeability. In the figure, the end P at which the direction of current is anti-clockwise behaves as the north pole, while the end Q at which the direction of current is clockwise behaves as the south pole. On reversing the direction of current on the solenoid, the polarities at the ends of the solenoid are reversed because the direction of magnetic field has reversed. Dissimilarity between a current-carrying solenoid and a bar magnet. Magnetic field lines of current-carrying solenoid. Magnetic field is due to the effect of current. Field disappears as soon as the current is switched off. Strength of magnetic field depends on the magnitude of the current. The strength can be changed by varying the current. Direction of field lines will change if the direction of current is reversed. Magnetic field lines of a bar magnet. Magnetic field has no dependence on any current. The field is due to natural magnetic properties of the magnet. Strength of field cannot be changed. Direction of field line cannot be changed. Electromagnet. An electromagnet is a temporary strong magnet made by passing current in a coil wound around a specific piece of soft iron. It is an artificial magnet. Usually the following two shapes of electromagnet are used. I-shaped electromagnet. Use. A bar-shaped electromagnet is commonly used in relay. Horseshoe electromagnet. Use. Horseshoe magnets are used in gadgets like DC motor, AC generator, electric bell, etc. Ways of increasing magnetic field of an electromagnet. The magnetic field of an electromagnet I or U-shaped can be increased by following two ways. By increasing the number of turns of winding in the solenoid, by increasing the current through the solenoid. Comparison of an electromagnet with a permanent magnet. Electromagnet, it is made of soft iron. Permanent magnet, it is made of steel. Electromagnet, it produces the magnetic field so long as current flows in the coil, that is, it produces the temporary magnetic field. Permanent magnet, it produces a permanent magnetic field. Electromagnet, the magnetic field strength can be changed. Permanent magnet, the magnetic field strength cannot be changed. Electromagnet, the magnetic field of an electromagnet can be very strong. Permanent magnet, the magnetic field of a permanent magnet is not so strong. Electromagnet, the polarity of an electromagnet can be reversed. Permanent magnet, the polarity of a permanent magnet cannot be reversed. Electromagnet, it can easily be demagnetized by switching off the current. Permanent magnet, it cannot be easily demagnetized. Advantages of electromagnet over permanent magnet. An electromagnet can produce a strong electric field. The strength of the magnetic field of an electromagnet can easily be changed by changing the current or number of turns in its solenoid. The polarity of electromagnet or the direction of the field produced by it can be reversed by reversing the direction of current in the solenoid. Use of electromagnet for loading the furnaces with iron, for separating the iron pieces from debris or ores, where iron exists as impurities, example, for separation irons from crushed copper ore in copper mines. For removing the pieces of iron from wounds. Electric bell. Electric bell consists of a gong, hammer, adjusting screw, electromagnet, armature metallic strip, battery and a switch. Force on a current-carrying conductor. When no current flows in the wire, no force acts on the wire and the wire does not move. When current I is passed in the wire in direction from A to B, that is in x direction, a force F acts on the wire in the direction perpendicular to both the direction of current I and the direction of magnetic field B. Due to the force, the conductor begins to move towards the observer or normal to the plane of paper in outward direction, that is in Z direction. If the direction of current through the wire is reversed by interchanging the terminal of the battery, the direction of force, that is the direction of movement of wire, is also reversed. On reversing the direction of magnetic field, that is on reversing the polarities north and south of the horseshoe magnet, the direction of force, that is the direction of movement of wire, is reversed as compared to now it moves in Z direction. Magnitude of force. The force F is directly proportional to the current flowing in the wire, that is F is directly proportional to I. The force F is directly proportional to the strength of the magnetic field B, that is F is directly proportional to B. The force F is directly proportional to the length L of the wire within the magnetic field, that is F is directly proportional to L. Therefore, F is equals to IBL. Unit of magnetic field. The SI unit of magnetic field is Newton per ampere meter. It is also named as Tesla, symbol T, or Weber per meter square. Fleming left-hand rule. Fleming's left-hand rule. Stretch the forefinger, central finger, and the thumb of your left hand mutually perpendicular to each other as shown in the figure. If the forefinger indicates the direction of magnetic field and the central finger indicates the direction of current, then the thumb will indicate the direction of the motion of the conductor, that is force on the conductor. Central figure C is equals to current. Forefinger F is equals to field. And thumb, which has M, gives motion. Simple DC motor. An electric motor is a device which converts the electrical energy into mechanical energy. Principle. A DC motor works on the principle that on passing electric current through a conductor placed normally in a magnetic field, a force acts on the conductor, as a result of which the conductor begins to move and thus mechanical energy or work is obtained. The direction of force on the conductor is obtained with the help of Fleming's left-hand rule. Ways of increasing the speed of rotation of coil: by increasing the strength of the current in the coil, by increasing the number of turns in the coil, by increasing the area of the coil, and by increasing the strength of magnetic field. Demonstration of electromagnetic induction. When the magnet is stationary, V is equals to 0, there is no deflection in the galvanometer and its pointer reads 0. When the magnet with its north pole facing the solenoid is moved towards it, the galvanometer shows a deflection towards right, showing that a current flows in the solenoid in the direction B to A as shown in the figure B. As the motion of magnet is stopped, the pointer of the galvanometer comes to 0 position, figure C. This shows that the current in the solenoid flows as long as the magnet is in the motion. If the magnet is moved away from the solenoid, the pointer of galvanometer deflects towards left, figure D, showing that the current in solenoid flows again, but now in direction A to B, which is opposite to that shown in figure B. Current becomes 0 as soon as the magnet stops. If the same action movement of magnet is done rapidly, the deflection in the galvanometer is more than before, although the direction of deflection remains same. It shows that now more current flows. If the magnet is brought towards the solenoid by keeping the south pole towards it, the pointer of galvanometer deflects towards left, figure E, showing that the current in solenoid flows in the direction A to B, which is opposite to that of shown in figure B. Conclusions. A current flows in the coil only when there is relative motion between the coil and the magnet. The direction of current is reversed and the direction of motion or polarity of the magnet is reversed. The current in the coil is increased by the rapid motion of magnet or coil, the use of strong magnet, and increasing the area of cross-section of coil, and by increasing the number of turns of the coil. Electromagnetic induction. Electromagnetic induction is a phenomena in which an EMF is induced in the coil if there is a change in the magnetic flux linked with the coil. In electromagnetic induction, the mechanical energy spent, that is the work done in moving the coil or the magnet to change the magnetic flux is transformed into the electrical energy in the form of current in the coil. Faraday's law of electromagnetic induction. When there is change in magnetic flux linked with a coil, an EMF is induced. The EMF induced lasts so long that the magnetic flux linked with the coil changes. The magnitude of EMF induced is directly proportional to the rate of change of magnetic flux linked with the coil. If magnetic flux changes at a constant rate, a steady EMF is produced. If the circuit of coil is closed, a current flows in it due to the EMF induced across its end. Factors affecting the magnitude of induced EMF. The rate of change of magnetic flux linked with each turn. The number of turns in the coil. Lenz's law. According to Lenz's law, the direction of induced EMF or induced current is such that it opposes the cause which produces it. Fleming's right hand rule. Stretch the thumb, central finger and forefinger of your right hand such a way that they are mutually perpendicular to each other as shown in the figure. If the forefinger indicates the direction of magnetic field and the thumb indicates the direction of motion of the conductor, then the central finger will indicate the direction of induced current. AC generator. An AC generator is a device which converts the mechanical energy into electrical energy. Principle. In a generator, a coil is rotated in a magnetic field. Due to rotation, the magnetic flux linked with the coil changes and therefore an EMF is induced between the ends of the coil. Thus, a generator acts as a source of current in an external circuit containing load when it is joined between the ends of the coil. Distinction between DC and AC. Direct current. It is a current of constant magnitude. It flows in one direction of the circuit. It is obtained from a cell or a battery. Alternating current. It is a current of magnitude varying periodically with time. It reverses its direction periodically with flowing in a current. It is obtained from an AC generator and mains. Distinction between AC generator and DC motor. AC generator. A generator is a device which converts the mechanical energy into electrical energy. A generator works on the principle of electromagnetic induction. In a generator, the coil is rotated in a magnetic field so as to produce an electric current. A generator makes up two separate coaxial slip rings. DC motor. A DC motor is a device which converts electrical energy into the mechanical energy. A DC motor works on the principle of force acting on a current carrying conductor placed in magnetic field. In a DC motor, the current from a DC source flows in the coil placed in a magnetic field due to which the coil rotates. A DC motor makes use of two parts of a slip ring, that is split rings, which acts as a commutator. Transformer. Transformer is a device by which the magnitude of an alternating EMF can be increased or decreased. Principle. A transformer works on the principle of electromagnetic induction and makes use of two coils having different number of turns. The two coils are named as the primary coil and the secondary coil. The alternating EMF, of which magnitude is to be changed, is applied across the primary coil and the appliance in which the output is to be obtained is connected across the secondary coil. When there is a change in the magnetic field due to varying current in the primary coil, the magnetic flux linked with the secondary coil also changes, and so an induced varying current of same frequency but of different magnitude flows in the secondary coil. For an ideal transformer, when there is no loss of energy, the output power will be equal to input power. That is, power in secondary coil will be equal to power in primary coil. ESIS will be equals to EPIP, but ES by EP will be equals to NS by NP. Thus, we can conclude IP by IS is equals to ES by EP is equals to NS by NP. Distinction between step-up and step-down transformer. Step-up transformer, it increases the AC voltage and decreases the current. It turns ratio more than 1. It has more number of turns in the secondary coil than in primary coil. The wire of primary coil is thicker than that of secondary coil. Uses at power generating stations with X-ray machine, televisions, etc. Step-down transformer. It increases the AC voltage and decreases the current. Its turns ratio is less than 1, that is, it has less number of turns in the secondary coil than in the primary coil. The wire of the secondary coil is thicker than that of the primary coil. Uses at power substations with night electric bulb, computers, electric bulbs, etc. Transformers and its uses. Uses of step-up transformers in transmission of electric power at the power generation station to step up the voltage. With television with wireless sets with X-ray machines to provide a high accelerating voltage. Uses of step-down transformers with electric bulbs, night electric bulbs, mobile phone computers, etc. at the power substation to step down the voltage before its distribution to the consumers. Power plant gives 12 kV. A step-up transformer is used, which further steps up the voltage to 400 kV. High voltage transmission line, then a step-down transformer substation is used, which further decreases the potential by 13 kV, and then a step-down transformer is used, which decreases the potential to 240 V before reaching our homes.